Hey everyone. So we have a really nice problem here dealing with topics in inferencing, kind of covering a lot of the stuff that we're seeing in chapter 10 and a lot of what we've seen in chapter 9. It's a really great problem, and so we're going to get right to it. This problem is actually 1035, and it's on page 569. The problem says, weekly sales of regular ground coffee at a supermarket have in the recent past varied according to a normal distribution with mean 354 units and standard deviation 33 units. The store reduces the price by 5%. Sales in the next 3 weeks are 405, 378, and 411 units. Is this good evidence that average sales are now higher? Well, we need to unpackage this question of, is this good evidence that average sales are higher? What this is in effect asking is the data that we're observing in this problem sufficient to reject what we believe to be the status quo of what weekly coffee sales are? And so what is that status quo that we're talking about? That status quo is also known as the null hypothesis, what we believe to be true just in the everyday scheme of things. And the null hypothesis, we believe, is that mu, the true mean of coffee sales, we believe to be 354 units. We're testing it against the alternative hypothesis, which is that mu is in fact greater than 354 units. Okay, and so this is what we're going to examine. We're going to use data analysis and statistics to be able to answer this question. What is the data that we need? We need to get a sample mean and a sample standard deviation. What does the sample mean? The sample mean is simply x bar, and as you know, to get x bar, you simply need to add up the values and divide by the number of values. Our data set is quite small. It only has 3 values. The values in our data set are 405 plus 350 or 378 plus 411, and that will be divided all by 3. When we divide by 3, we'll get that the mean x bar is 398. Now, what is S? What is our sample standard deviation? Well, in this case, they tell us that S should remain constant as sigma. So S should remain constant as what we know to be the true sample standard deviation. So, S is kind of nullified in this case. We're going to see examples later where S is not, but in this case, we can kind of effectively forget S and just think about sigma. Sigma is going to remain constant at 33. There is no variation. We won't see any variation in the sampling, so we just leave it as 33. Great. We, however, cannot take statistics yet because we're not drawing from really the true distribution. Remember that every time we draw a sample, it's like we're drawing from all possible samples of size 3. Sampling is random. We may get this particular sample, or we may get different ones, or we may get slightly bigger, slightly smaller. So we have to be thinking about what is the distribution of possible samples. In other words, what is the possible sampling distribution that we can draw from and make inferences from? Well, to be able to construct that, we need something called the central limit theorem, or the CLT. And the CLT tells us what the parameters of a sampling distribution should be. Okay, so if we look at the CLT, it tells us that if we want the mean of x bar, if we want the mean of the sampling distribution, this should be equal to the mean. We believe that on average, our guesses should be centered on what the truth is. And so we believe that mu of x bar should be equal to mu, which is also equal to 354. Okay, what is sigma of x bar? Well, it's almost the same, but it's a little bit different. Sigma of x bar will be equal to sigma divided by root of n. And so what that's saying is that we first of all believe that the sample standard deviation should be close, or it should be related somehow to the true standard deviation. But we also believe that the variation on our observation should decrease every time we increase the sample, just because we're going to be less uncertain with the more data that we get. So what that means then is if we want the sampling distribution of x bar, we just need to take the original standard deviation and divide it by root of n, okay? And in this case is 3. There's 3 values in the data set. And so 33 divided by root 3, if you crunch that, that's going to get 19.05. Okay, so let's draw that. We've got our 2 parameters, mu of x bar and sigma of x bar. What does that look like? Keep in mind too that the central limit theorem is so powerful because it's going to tell us that the sampling distribution is itself going to be normally distributed. And that's because of one of 2 things. Either if n is greater than 30, or if the original distribution that we're drawing from is itself normal. And it is, that the second case applies. The first doesn't, but still it will be normal. Okay, so it's normal. It's going to look like that familiar bell curve. The bell curve should be centered on 354. Okay, and a standard deviation, which would describe the variation of the bell curve. Okay, if we move one out, we're going to just be adding 19.05. Okay, and so if we move one out, if we move one standard deviation to the right, like so, it's going to move it up to 373.05. So let's get a perspective of the value that we are observing, and we can use this to be thinking about inference. Okay, so the value that we're observing is right here at 398. And this is the likelihood of observing that. As you can see, the area that I'm shading under the curve is very, very small relative to the rest of the curve. Okay, and so we can be thinking about that, and we can be thinking about what does that mean in terms of inferencing. Well, we're saying that given this bell curve, this is all, by the way, assuming that H naught is in fact true. And assuming that H naught is in fact true, and we've just gotten this value by chance, really, well, the chance that we could have gotten this value is going to just be really, really small. It's just going to be the area under the curve that you see there. And so given the unlikeliness of observing an area under the curve this small, we're going to make an inference, and we're going to say, well, it wasn't really by chance that we got such a small probability. It's probably more likely that what we believe to be true is in fact not true. And that the real mean, because what we've observed is so much bigger, the real mean is likely higher than what we believe the true mean to be. Okay? And so that's what we're seeing in the graph. That intuition makes sense. Okay? The reasoning, the inductive reasoning really makes sense. Okay? Let's just use some math to finalize what we're thinking right here. Okay? So we just need a few more mathematical calculations. What we need to do is we need to find the probability that the given value that we've observed is greater than some sort of standardized normal value. We need to see how many standard deviations away from the mean our x bar is. So we need to take x bar and subtract it from mu and divide it by those sample standard deviations, and that's why we're divided by sigma divided by root of n. Okay, and so what we're trying to see is we want to see the probability that we could observe a value greater than 398 minus 354 for our hypothesized mean, divided by 33, the standard deviation, over root 3, because our sample size is 3. Okay, so we've standardized this value, and because we standardized it, it's going to fall under a z distribution. Okay, so what we want is not z, but, or you know what, actually, let's leave it as z. Okay, because we are drawing from that z distribution. Okay, we have the probability that z should be greater than 2.31. In other words, we'd like to know that given this standardized value, what is the probability that we could see a value 2.31 standard deviations above the mean or greater? What's the likelihood of that happening? Well, keep in mind too that when you have a z greater, okay, not to be confused with greater than, so I'm going to take that away, but you get what I'm saying here. If we have a z greater than 2.31, what we're in effect saying is we'd like to know what is 1 minus the probability that z is less than 2.31. That's how you kind of like trick the system into giving you the actual probability that you want. So if we ask this question, now the calculator, or now the book, if you're using the book, could give us the probability value. This is the same as 1 minus, well, if you look at the book or if you look at the calculator, the probability that you get a z value less than 2.31 is in fact 0.9893. And if you crunch that out, your final probability is 0.0107. This is also known as our p-value. Okay? And what's a good definition of p-value? P-value is simply the probability that we could observe this value as extreme as or more extreme given that the null hypothesis is true, and assuming that. So assuming the null hypothesis is true, we have a probability of about 1% that this could have happened. Not very likely. So let's go to our final conclusion. Our final conclusion is that since 0.0107 is less than 0.05 but not less than 0.01, we can reject the null hypothesis. We have sufficient, but not highly sufficient evidence to believe that coffee sales are greater than 354 units per week. And that's what we saw in the data, that's what we saw graphically, and that's what we're seeing mathematically. So let's unpackage this whole conclusion. There's actually 3 important steps I want to cover. Okay, the first step is what you call linkage. Okay, so this is called linkage. And linkage simply means that we're going to use some sort of mathematical statement to validate what we're saying. We're saying that we get this p-value and it's less than the threshold of what we've set alpha to be. Alpha in this case is 5%, or maybe we set it as low as 1%. But since it's lower than that, we're going to get right to step 2. Step 2 is our decision. So our decision tells us, do we reject or do we fail to reject the null hypothesis? And it appears that we're going to reject H naught. Okay? Once we get that, we get to our final step. We have sufficient but not highly sufficient evidence to believe that sales are greater than 354 units per week. What this means is that this is the conclusion in context. Because we could just say reject H naught, but what does that even mean? You know, especially in the context of the problem, what is that actually saying? Okay, now we know what it's saying. We're saying that we thought the coffee sales should be 354. We thought that that's what the truth is, but that's not the truth. According to the data, coffee sales are actually